So to progress in this field, we partnered with Scalable Network Technologies to provide a solution to the market. So as many of you might already know, so at OPAL-RT, we're experts in real-time simulation of power systems and power electronics. And Scalable, and they are experts in real-time simulations of communication networks infrastructures. So it was quite a good fit to be able to provide the best-in-class real-time cyber-physical system simulations. So this here is the solution that we've been working on together. So you see on the left side, we have HyperSim for the power grid. On the right side here, we have Exada CPS that's running the communication network emulation. And both communicate together via a virtual communication link as they are running on the same target simulator. So to achieve real-time performance, each of the two tools are running on dedicated cores. As I said, they exchange information over a virtual Ethernet interface before the messages can be sent out through the physical ports of the simulator to interconnect with external devices such as PMUs, SCADA system, human-machine interface, protection relays. So exactly as it could already be done with HyperSim, but this time also simulating the communication network along with the power grid to get a higher accuracy. So here's a quick example. So you can see the Exada GUI on the left side, the HyperSim on the right one. And here's a quick list of the available cyber attack types that can be programmed and tested using this solution. So denial of service, passive attacks, jamming, packet modification, virus, swarm propagation, rootkit, and many more. And we'll have a quick demo very soon to show you the capabilities of the software. So for the demonstration, we have a microgrid that's designed in HyperSim, where we have the utility grid on the left, the point of common coupling right here. We have critical loads, industrial loads, residential loads, a couple of DER, so PV, battery energy storage system, PV, CHP, and they all communicate with the microgrid controller using IEC 61 and 50 Goose messages, and they're all connected to the same switch. And we'll also have a dashboard for which we use the Xenon software and with which we communicate over OPC UA. We'll have two scenarios. The first being when islanding the grid, we're going to have a delay attack. So what we do when we island the grid here, as there's not enough generational power for all the loads, we need to shed this load here. So this happens automatically by the microgrid control. And where we're going to attack the Goose message that goes from the microgrid controller to this circuit breaker here and put a delay on it. So we're going to see what effect it can have on the grid. The second scenario is while the grid is islanded, we're going to attack the power measurement value that is sent from this industrial load to the microgrid controller. We're going to double it. So the microgrid controller, again, is going to think that this load is pulling twice as much power as expected. And in response, as there's not enough generational power again, it's going to disconnect load number 3. So we're going to move to the live demonstration. You can see here, this is the power grid in HyperSim. We have all our DERs simulated. We have the communication network that's simulated here in Exada CPS. The interface between the two is done via a mapping file, so you can easily connect all the nodes that are here that represent the DER can be found in a drop-down list here. This is provided by HyperSim when modifying the IO configuration. This file is generated automatically. That when it's provided to Exada CPS, we get these drop-downs so we can easily map the different DERs to the communication network. And once the model is ready, you can launch the scenario player. So we see here, this is a 3D representation of the power grid communication. You see all the red dots, they are the communication that happen between the different DERs. I'll pull up the Xenon dashboard here. So the simulation is running. We're measuring the frequency here on the left and the voltage here on the right. You'll see if I island the system, those two breakers open at the exact same time. As I explained, we need to shed this load as there's not enough generational power. So I'm going to reconnect to the utility grid. We're going to go to the scenario player again. I'm going to zoom in to node 59, that is our microgrid controller. And through a right-click menu, we have access to all the cyber attacks that are possible to send. We have pre-configured already an attack of delay of 5 seconds. So you see here, we're going to attack the load number 1, it's circuit breaker. We have applied a delay of 5 seconds. I'm going to launch this attack. We're going to go back to our Xenon dashboard. And when I click on islanding the grid, you'll see here that there's a long delay here with the frequency drops below the threshold that has been set. The voltage also drops much lower. So you can easily extrapolate to potential damage that can happen to the grid, backup protection kicking in. But obviously, this has a serious impact on the microgrid. We're going to go to our second scenario, but first I'll just stop this first attack here. We'll go to the delay, stop the modified packet attack, and we're going to go to load 19, which is our load. And we're going to apply the multiply attack. Same principle here. So we select the load 2, multiply by 2. In this case here, we attack specific bytes in the goose message. We start at byte number 113. For 2 bytes, we multiply the value by 2. And going back to the dashboard, we'll see here that this circuit breaker is flickering. Basically, we implemented a reclosing algorithm for the demo purpose. To better show that as long as the attack is ongoing, if we try to reconnect the load, obviously there's not enough generational power, so the microgrid controller is sending again the message to reopen this circuit breaker here. That's all for my demo.